¿Lo veis?
Sí.
Sí.
Perfecto, además a la primera. Vale, pues bueno, gracias por la presentación. Aunque he visto que muchos de vosotros sois españoles, el seminario y las diapositivas están en inglés, pero vamos, supongo que esto no va a ser ningún problema. Y bueno, bueno, voy a cambiar de idioma, ¿vale? So, now, change mood, we switch to English. And as Maria said, the topic of this seminar is going to be about searches for new particles beyond the beam spot. So let's, okay. So setting the scene. So as Maria said, in 2013, I was a fresh CIEMAT PhD student working in CMS. And here just I wanted to show a picture from that time. So this is the first time I went down to CMS. And so I'm very happy of this time at CIEMAT. Completed the PhD, and then since 2017, I'm a postdoc at HEFI. Also in CMS, but I changed a little bit the topic. And since 2017, I'm working on long-lived particles. And this is the topic of this seminar. So I'm going to first briefly introduce BSM searches in CMS. Then I will talk about long-lived particles. And then in the second part of the talk, I will get more into detail and then talk about 5 selected examples. They don't need to be the latest, but searches of long-lived particles in CMS. Finally, we'll conclude with the prospects. So this talk is going to be, I hope it should be fairly, at least easy to digest the beginnings. So this was keeping in mind that the audience is not CMS people. So let's start, and all begins with the LHC. So here I wanted to quote some metrics, some important numbers for the presentation. And then in the period of 2015 to 2018, Atlas and CMS have recorded about 140 inverse defense barn. So here this plot shows the integrated luminosity as a function of the time for each of these years. And you can see how the luminosity is distributed across the time. To put this into context, this is about 7 times the luminosity compared to the Higgs data set. Now the center of mass energy was higher with respect to discoveries, so 13 with respect to 8. And in terms of a physics quantity, this amounts to about 7 million Higgs bosons. Then another important quantity that I wanted to highlight is called instantaneous luminosity. This is a metric of the amount of collisions per unit of time, again, as a function of these all 4 years. And then I want you to draw your attention to this horizontal line, and this is the value or the design value of the LHC. And as you can see, the LHC has been operating since 2016 at the higher instantaneous luminosity than the design value. So just, it's fair to say that from LHC side, the output was better than expected during this time. Now we are in shutdown, and then we will start taking data for the Run 3 in 2022 up to 2024, and this is pre-COVID. So getting into the topic of this seminar, that is beyond standard model searches. And essentially, since the beginning of Run 2, the motivation to search for new particles at the LHC hasn't really changed. So the same questions still hold, such as what's the nature of dark matter, origin of neutrino masses, why 3 generations of leptons, quarks, sources of lepton flavor violation, lepton flavor universality, or grand unification of forces. I don't mean to say that all these are going to be answered at the LHC, but these are motivations to search for new particles. Then going to CMS, the way the BSM searches are done in the experiment is that they are first broadly divided in terms of their interpretation. So we have these 4 big groups that are going to be SUSY, that are called searches for supersymmetry. We have Exotica, that are essentially searches that are not supersymmetry. Beyond 2 generations, that are searches involving the top anti-boson resonances. And then we have the Higgs, that includes measurements and also searches involving the Higgs boson. Then within each of the groups, then the searches are further subdivided in terms of the final state. And this is a rather experimentally driven categorization. Then I wanted just to highlight that all these searches, they have a common denominator, and is that they all test standard model prediction in different corners of the phase space. So somehow, even they search for new particles, they are still, in a way, measurements of standard model processes. Putting a bit searches in the context of the CMS physics program. This plot shows here the number of publications as a function of the time for the different groups in CMS. And I discussed these 4 here. And we see that as of last weekend, we have submitted about 993 publications. And if you make the numbers, about 50% of all publications, including round 1 and round 2, focus on searches or have as primary goal the Higgs boson. This means that searches is a big thing in CMS. So now going to a bit some of the highlights of these results, starting from supersymmetry. And for this, I'm going to take gluino. This is one of the supersymmetric predicted particles. As an example, what are the results? And typically, you would see these summary plots where you have in the vertical axis the production mechanism and the decay of the gluino in this case, and then further subdivide into the final state. And here the bars show what mass has been excluded. And you can see that there are many searches, and this is, as I said, the example of the gluino, but this applies to all the SUSY particles, and there are no signs of SUSY across the searches. Then the second big group is exotica. This would include, for example, additional gauge bosons like C prime, W prime bosons. The structure is the same. Now it's harder to read because there are more searches, but then you can see what mass has been excluded, and I tried to match the colors. So all these are additional bosons. You have also dark matter, you have leptoquarks, and also we had, you have heard about biphoton resonances where there was an excess in the past. And long story short is that after run 2 data, there are no signs of physics in, I'm going to call inclusive SUSY and exotica searches. And then later I would explain what this means. And then finally, we have the Higgs boson, where the situation is different because indeed this has been observed. And this is probably the main highlight of the round 1 and round 2 data. So as of today, the coupling to the 3rd generation of fermions, the top, the bottom, the tau. Now there is also evidence to 2nd generation fermion, this would be the muon, and then the coupling to the WC and the photon, they have all been observed. And so far, they have been all in agreement with standard model predictions. To show a plot for these results, this is a histogram of the 4 muon invariant mass. So this is the number of entries. This is one of the decay modes of the Higgs boson. And then you see around the mass this peak. So this is the production of the Higgs. And this is great that the Higgs has been observed, but one should also say that the Higgs discovery did not provide an answer to some of the questions that I mentioned already. And yet it opened new ones. For example, is MH fine-tuned? Is it elementary or composite? What is the origin of the Higgs potential? The role in the neutrino sector? Or if it couples to a dark sector? Or now that we just saw evidence for the muons, why there is a hierarchy of particle masses. And then from the experimental point of view, it opened the field of searches for new physics in the case of the Higgs boson. They are also called exotic decays. So with this in mind, now the question in view of round 3 is where is the new physics at the LHC? And now searches are aiming, well, let me call it future and ongoing searches are aiming to extend beyond traditional, instead of traditional, I would call them inclusive approaches. And what this means, and here I want to quote some examples, is that for exotic and SUSY searches, now they try to target challenging regions of the phase space. And for instance, this could be final states with low PT objects. And this is typically something that you have if you have a compressed or you have mass degenerate BSM states. You can have final states without missing transverse energy. So for example, SUSY searches without LSP, or in exotica, you just move away from resonances. You can also target precision Higgs stop or standard model measurements. And in particular, something that is now an interesting topic is to look for deviation in high PT tails across different searches. So a Higgs measurement and a standard model measurement or a top measurement. And then see if there is a common BSM scenario that could fit all of them. And then I already mentioned searches for exotic Higgs decays. Now, in this seminar, so these are all really good approaches. I want to tackle a more wider question that is, if there is any class of experimental signatures that were not extensively covered in the past. And then in relation to this, I want to discuss if the BSM parameter phase space is completely covered with the current searches. And to start to address these two questions, one thing that I would like to remind is that many searches that I've discussed so far assume that BSM decays to combinations of two well types of well understood objects. And these I'm going to call prompt objects. These are going to be charged tracks, electrons, muons, taux, photons, or jets. And what is common to these is that they are produced within millimeters with respect to the beam spot. And then other possibilities to have undetected objects that are usually observed in the form of missing transverse energy, such as neutrinos or neutralinos for the case of BSM. And in general, in all these searches, any other object that is reconstructed is usually ignored, or this is vetoed if this can be a source of a background. So now the question that I want to bring is, what if this assumption is relaxed? And this brings me to the topic of this seminar. This is long-lived particles. And what I'm going to assume from now on is that what happens if BSM particles can travel macroscopic distances before they decay. I'm going to define what means macroscopic distances, because this is going to be done in the context of a detector, CMS in this case. And here, let me just highlight in this sketch the size. This is going to be connected to the lifetime and the different regimes. So prompt objects are produced inside the beam spot, and then stable invisible particles will not decay or decay at the end of the detector acceptance. So this is 10 meters, and then prompt objects are within 1 centimeter. Everything that decays in the middle, and this is not to scale, this is what I'm going to call long-lived particles. And searches for these particles is what I'm going to call searches beyond the beam spot. And now with this assumption relaxed, we see that only 6% of all the searches assume that BSM particles can travel and they might decay at macroscopic distances. Now, because we have all searches and an additional parameter that can be the lifetime, the phase space becomes very large. And in particular, the lifetime is often a tunable parameter in the theory. So this is something that just explodes the number of final states or topologies that you can build. And of course, this makes it a largely unexplored territory. So now you might wonder if we should worry about searching for this type of objects, for long-lived particles. And I would try to give some arguments why they should not be ignored. The first one is that standard model contains long-lived particles. And here this plot shows the lifetime as a function of the mass for the different standard model particles. And as you can see, the lifetime spans over many orders of magnitude. In particular, the lifetime of some standard model particles were critical for the design of CMS. And here I'm talking about, for example, the tau or the bees, because the inner tracker is designed such that their decays happen before the first pixel tracker layer. Or for instance, the Higgs boson has a very short lifetime that is prompt. So the question is why one cannot have such a complicated lifetime spectrum also in BSM physics. So in principle, there is not a deep reason to exclude this possibility, given that it also happens in standard model. But to give a bit a more solid answer, let's maybe review what gives a long lifetime to standard model particles. And to keep it as short as possible for a particle to be long-lived, so the lifetime essentially is the inverse of a particle width. And in order to have a large lifetime, what you need is a small width. And in order to have a small width, what you need is that this integral is suppressed. So you can suppress this by suppressing the phase space or by suppressing the matrix element. And there are different mechanisms or different ways that you can do this. The first one is to have decays of particles mediated by heavy virtual mediators. So in the standard model, this could be the case for the muon, for instance. Or you can have decays between two states that have small mass splitting. So this would be the case for the muon. Or you can have an interaction that it has a very small coupling. So this also could be combined with other mechanisms, but this would be the case of B hadrons, for instance. So usually one can see, if one computes this width, one can identify some of these terms. So this is a generic formula, but you can identify terms like this for the width, where you have the couplings, you have a mass hierarchy, where you have here the mass of the mediator, and this is suppressed by some power depending on the gauge symmetry, or it depends on the symmetry of the model. So for the case of the pion, this is the full lifetime formula, and then you can connect some of these terms like the coupling. You have the mass hierarchy between the W and the mass of the pion, and then the mass difference between the two states. And as you can see, if you make the mediator to be very heavy, as for the case of the pion, then you can get a large lifetime. So these mechanisms that apply to standard model can also happen in BSM models in different regions of the phase space. You just have to sit in one of these areas. So in order to illustrate this, I want to give some example of BSM models with long-lived particles that are discussed in theory. The first one, and I will try to connect them with some of the open questions in particle physics. The first one is generally called heavy neutral leptons. And this can be seen as a heavy neutrino that mixes with the standard model neutrino. And the reason why you want to have these is to address the neutrino mass. So the way this is done is with the seesaw mechanism that connects the smallness of neutrino mass with a heavy neutral lepton, or with a heavy neutrino. And the reason for a large lifetime in this case is that the decay of the heavy neutral lepton would be mediated with a heavy mediator. This would be the W, and then you expect to have a small coupling with the standard model neutrino. So typically, the way this is tested at the LHC is that you have standard model W production that it decays to neutrinos, that mixes with the heavy neutral lepton, here denoted as capital N, and because this is lighter than the W, then this becomes long-lived. And here, this plot on the right, it shows the lifetime. So this is the lines in the plot as a function of the mixing between the HNL and the standard model neutrino and the mass. And as you see, as you approach the bottom of the diagonal, so small lifetimes and small masses, then the HNL becomes long-lived. So for instance, this line of 100 nanoseconds, this is already a decay outside CMS. So this is an area that is targeted at the LHC, and in particular in CMS. Second example is a dark photon. So this is widely discussed in different fields, and often this is denoted with different letters like A, C dark, gamma dark, and many others. And the motivation to introduce a dark photon, this is as a mediator between a dark sector that would include a dark matter candidate and the standard model. And one of the properties of photon is that it's very weakly connected. It has a very weak couplings between the two sectors. So that it's very hard to have interaction between standard model particles and dark sector particles. And then the strength of this connection is mediated with the kinetic mixing, here denoted by epsilon. What is done in practice is that one extends the standard model with an additional U1 symmetry that mixes with the hypercharge, and you get this term, and then you get here the kinetic mixing. In practice, there's a relation between the strength of the kinetic mixing and the mass of the C dark, and that leads to the lifetime. So again, in a similar spirit as before, as you go to small kinetic, as you go to small kinetic mixing here between, say, 10 to the -6 or 10 to the -8, and then a small mass, you can have lifetimes that are quite large. But these are macroscopic lifetimes. What happens is that often, if this strength is very small, if this coupling is so small that this becomes long-lived, it becomes really hard to produce at the LHC because the cross-section is so small. So this is also something that one should keep in mind. So then people have worked on more complex dark sector models. They are often generically called Higgs portal models, where one can produce dark photons in Higgs decay. So if you have just a minimal mixing, then you can produce seed arcs in a standard drilling process, and this alternative mechanism would produce pairs of dark photons in rare decays of the Higgs, because there is now a mixing of the standard model Higgs with the dark Higgs. This is what controls the production of dark photons. So this is also an interesting model that is widely discussed in the field of long-lived particles, because it gives a unique signature of a LHC. And then the third example of a long-lived particle, and this I wanted to highlight for two reasons. The first one, because it's SUSY, and usually people say SUSY is dead. And the second one is because it's a charged object, because long-lived particles could be charged as well. In this case, the long-lived particle is a chargino, and the property that it has is that it's mass generate with a neutralino. And here the neutralino would be a dark matter candidate. The reason why this is motivated is because of SUSY or the dark matter problem, so any of the two. And the reason why the chargino is long-lived is because its mass generate at tree level with the neutralino, but then once you go to 1 and 2 loop correction, this introduces a small mass splitting. So this mass splitting is of the order of a few hundred of MeV for a neutralino of a wide range of masses. This is a prediction from the theory. And because of this small mass splitting, this, as I said, a prediction of the theory, then you can have a lifetime. So this is the plot on the right, also as a function of the mass. Now it's the mass of the chargino. You get a typical lifetime that is of the size of the tracker of CMS. So if this object is produced, it's likely that you would produce a chargino, and then somewhere in the middle of the tracker, it would decay to a neutralino and, for example, a pion. So this is a typical production mechanism. So this is a long-lived particle that just decays in the middle of the tracker. So this is one of the other signatures that is also tested in searches. So I discussed 3 examples of BSM theories. These are not the only ones. These are not necessarily the best ones. So people have worked in many other theories with long-lived particles that try to connect some of the open problems like neutrino masses, dark matter, naturalness, with some scenarios with long-lived particles, so such that more or less for most of BSM models, one can try to find the region of the phase space that one can find long-lived particles. So this is a summary taken from this paper, but the message to take here is that long-lived particles are not rare objects. They appear in many BSM scenarios in different regions of the phase space due to these mechanisms that I mentioned. And what is important for this presentation is that they have not been extensively explored experimentally. So from now onwards, I'm not going to talk about theory anymore. Instead, I will take an experimentally driven approach. And then for this, I'm going to take the lifetime as a free parameter. Because as I said, usually this can be tuned in theory. And what this means is that the long-lived particles can decay at any geometrical point of the detector. I will not make special assumptions. What this means is that also this is going to lead to some unconventional signatures. So as I said, this could be any point of the detector. So maybe let's remind the structure of CMS, because I will discuss CMS results. So here I show longitudinal view of CMS, and here a transverse view of CMS. And here in different colors, you can see the different sub-detectors. So starting from, so collision point is here, the beam spot is here. So you have the tracker for charged tracks. You have the electromagnetic colorimeter in green here. So this is, for instance, to detect and measure photons. The HCAL for jets. So this is already a meter time scale. This is in a meter of displacement. And then you have the muon detectors already several meters away surrounding the colorimeters. So as I said, long-lived particles can decay at any point here, because I said I will not make any assumption. So here you can see the same detectors, the tracker, colorimeters, and then the muon detectors in the transverse view. So one important point that I want to highlight is that often, as I said, standard model objects typically decay within the beam spot, which means that often the algorithms like the triggers, reconstruction are optimized for objects or Sada model objects that point back to the primary vertex and are produced within the beam spot. But the problem or the difference is that long-lived particles are displaced and they often need a special treatment because the algorithms are not designed to work on these objects. And this is going to lead to some challenges in searches for long-lived particles. Because one question that you might wonder is, where do long-lived particles decay? And the answer is that this is unpredictable. And the reason for this is that the decay of a long-lived particle is a Poisson process that follows an exponential distribution that depends on the lifetime, but also on the boost or the momentum of the particle. Just to give an example, just two illustrative examples, this is so the distance traveled of a long-lived particle of a lifetime of 5 centimeters, and this is how the decay is distributed across the different subdetectors. So for instance, if the lifetime is 5 centimeters, you can have decays that are prompt. You can have decays in the tracker, in the calorimeters, in the muon system, and in some cases outside the detector. And then if the lifetime is larger, then you can have a sizable decay in the muon system or outside of the detector. What is important is that the lifetime, as I said, is a free parameter. This implies that there is not an ideal detector that can fit all lifetimes and boost combinations. So just the way that is designed CMS is going to work better for certain type of lifetimes. So this is something that we have to deal with this. And the way that long-lived particle searches are designed to protect against these or protect against over searching is to be as inclusive as possible, just to have as few requirements as possible to be as sensitive to any decay. Because for these cases, the standard model backgrounds are quite small. But then, and now I move to challenges in long-lived particle searches. The devil is in the details. And as you know, in CMS, but also in Atlas, not all collisions can be recorded. Just the rate is too high. And the system that decides which collisions are recorded is called the trigger. So this is made of two systems, the level 1 and the HLT system that produces the collision rate by selecting the collisions in two steps. The first one reduces the collision rate of 40 megahertz by a factor of 1,000 without tracking information. And this is a purely hardware-based system. And notice how this can be a problem if you want to select long-lived particles if you don't have tracking. So this is already a problem because you cannot access to how displaced they are already at the inner detector. And then the second level reduces the factor another 100 factor, and this is the high-level trigger. And here you have tracking information, and this is software-based. So the challenge is that there is a 10 to the 5 rate reduction while you have to keep the long-lived particle signal. And the problem in many searches is that long-lived particle signatures are just not selected by standard prompt triggers, and often they need a dedicated level 1 or HLT algorithm. And in some cases, even they would need a detector upgrade because CMS was not designed to detect very displaced objects. So this is a real experimental challenge. And just to mention how important this is, often improvements in existing level 1 or HLT triggers for long-lived particle searches can be better than accumulating large luminosities in some cases. So here there's really area for improvement. So now, going more to the searches themselves in CMS, there is what I call the zoo of long-lived particle signatures, is that depending on how a long-lived particle decay, you can have different signatures in the detector. So maybe just connect with standard searches where you usually look in production mechanisms, spin. Now we also have the lifetime. Long-lived particles can also be charged or neutral. They could be heavy or light. It can be relativistic or even non-relativistic. And in some cases, they can get trapped in some part of the detector and decay at a later time. And then they can decay into all different final states that are considered in prompt searches, like lepton, quarks, photons, gluons, or invisibly. And what is important is that each combination also with the lifetime, defines in most of the cases an experimental search that often requires a dedicated search. And then in the next, I'm going to describe 5 examples of signatures. So here the plot shows how these signatures are called. I'm going to go into this, so you don't need to remember all these names. So I'm going to describe 5 examples from CMS that use a different strategy or a different subdetector to search for a long-lived particle. And the way I'm going to do this, I'm going to jump from inside of CMS to the outside. And just as I said, I'm going to pick one example for each subdetector that we can have a taste of how these searches work. So I'm going to start by decays inside the tracker. So this is going to be the shortest lifetimes. And here we're going to benefit from this is going to be decay. The one I'm going to discuss is going to be decays in the inner tracker. And here put a picture of the inner detector and the beam pipe. This is a picture of the tracker outer barrel. And then what this is going to rely also is on the solenoid magnet, because this is going to bend the tracks and they're going to be measured in the tracker. So these are the main actors for this type of searches. So how searches in the tracker are performed? First of all, they have to decay inside the tracker. So this is only possible for decays up to 1 meter in radius and 3 meters in length. And this is just the tracker size. And depending on where they decay, different searches are performed. So for example, for the shortest lifetimes, there is a search for displaced vertices. So this is produced really before, so this is a size of the tracker. So these are decays even before the pixel, and then even before the beam spot that is not being shown here. Then you have the pixel detector up to 10 centimeters. So this is the red here, and then you have the tracker outer barrel that goes up to 1 meter. So the main variables that are used for searches used in the tracker are 2. One is a displaced vertex, so you can reconstruct tracks and fit a vertex that is going to be displaced with respect to the primary vertex. So this is where the collision happens. So this is how the long-lived particle would travel. And then the second variable that is used typically is the impact parameter. That this measure is defined essentially as the distance. So you propagate the track to the beam spot, you propagate the track back to the primary vertex, and then you take the perpendicular at the point of closest approach. This is how it is called, and this distance is called the impact parameter. So this is usually large for displaced objects. And the challenges for searching for long-lived particles inside the tracker is, well, the 2 main challenges are, first one that I already mentioned is that the tracker information is not available in the level 1 trigger. So you cannot use the tracker to select long-lived particles to select events. And then second of all, you have a large background from QCD processes. This means that it's very hard to probe low mass long-lived particles in hadronic final states. So there are almost no experimental constraints of low mass long-lived particles in hadronic final states. So let's go now to the first result, to the first example that I'm going to discuss. And these are pairs of displaced vertices inside the beam spot, so up to 2 centimeters. And the example or the model that they used in this search, this is the per production of gluinos or neutralinos. So this is a long-lived particle, and then it would decay after some time to jets. So essentially you would have 2, so you can see at this sketch, you would have pairs of jets produced at some distance. And then these pairs of jets would emerge from a vertex that is not the primary vertex and it's displaced. And the features of these 2 vertices is that they are made of multiple tracks that do not point back to the beam spot and form a displaced vertex. And this is different than the typical QCD background, is because for QCD, you have a much lower track multiplicity, and then the vertex is very close to the beam spot. So what is used to distinguish a signal from the background, the metric that is used is called this DVV, and this is the distance between pairs of displaced vertices. So this is this line connecting the two vertices. And you can see in gray here the QCD background, and then in all these lines, these are long-lived particle signatures for different lifetimes that you see that this distance is much larger. So there is nothing has been found, like no events have been found. Well, they were compatible with the background, and then you put, typically you put a limit for a given mass. You put a limit on the cross section as a function of the lifetime for a given mass of the long-lived particle. Before discussing the limit, just let me have discussed first the next slide, because I'm going to discuss commonalities of these limits. And I've titled this slide Demystifying Long-Lived Particle Results, because this can be a bit harder to read at first, because upper limits in LLP searches usually have well-defined regions of sensitivity. So in every LLP limit plot, it should be possible to identify some of these regions. Typically, at small lifetime, you have that searches lose sensitivity. So this would be a limit on crossing and in the lifetime. And this is because it mixes with the PROM, some other processes, and then this is just buried in the background. So it's not displaced anymore. When you go to the other side, you go to high lifetime, typically the LLP decays outside of the detector or in other sub-detectors. In this case, it can decay into a calorimeter for the previous example. Or just triggering is not possible. So usually you would lose sensitivity at high lifetime. And then the other factor is the mass of the long-lived particle. So typically trigger efficiency is more performing for certain type of masses. So as you move across masses, then this limit will upscale or downscale depending on the mass. So let me connect the limit plot with what I just discussed. We see that as you approach less than 1 millimeter, then you get the background from QCD, you lose sensitivity rapidly. As you go above 2 centimeters, that is the beam spot, again, you lose sensitivity rapidly because the decay is too far. And you see that this plot is picked for 800 GeV. And the reason is that it's very hard to go to lower masses because the trigger that is used in this search, because this focuses on high masses. Okay. So now I'm going to move to the second example. This is charged long-lived particles in the inner tracker. And then here, the main property is that now it's going to be a charged long-lived particle. So this can be a chargino, heavy muon, a fractionally charged particle. And what is important is that it can interact in anomalous or unexpected way with the tracker material. So this is typically what the way this is measured is with the DEDX. This is the energy deficit per unit of length. And this will depend typically on the charge, the momentum, or the mass of the long-lived particle. So here, the plot shows a quantity that is a proxy for DEDX. It's called here IH, as a function of the momentum of the particle. So here we have standard model particles, and here we have in red, pink, and green examples of 3 long-lived particles. And you see that the way they interact with the detector is just very different. So for example, here in green, where we have the largest difference, is that this is a particle with charge 2. So then this goes as the square, and then you go, this magnitude goes from 4 to 16. So this is a really striking interaction with the detector. And you can have 2 types of this type of charged long-lived particles. If they're stable, usually they're called heavy stable charged particles. So this is just a stable, massive, possibly with a different charge that travels in the detector. I titled this as "Who Ordered That?" because this can be seen as a heavy muon. So this is quoting the sentence when the muon was observed. And then if the charge long-lived particle decays inside the tracker, this I discussed, this could be the chargino, then the track, especially if there is a small mass splitting, it can disappear. So you have a charged track that just disappears. So this is the other type of charged long-lived particle. And this is the case I'm going to discuss. So the scenario that I discussed in the theory introduction is that you can have a long-lived chargino that decays, that is long-lived due to a small mass splitting. And typically what you have is a chargino that travels and then decays into a soft pion, an invisible particle that is not reconstructed. So effectively, these two particles are not observed. So you have a charged particle that just disappears due to the low momentum of the decay products. And if you try, so you can build a quantity that is called the number of missing outer hits. So you can reconstruct the chargino tracks and compute how many tracks, how many hits the track should have, but compared to the ones that you observed. And then the chargino, because you often miss the outer hits because it has decayed, this can provide a powerful signature to distinguish a track that has disappeared. So this is how this type of objects are measured. And this is the results. So these are the constraints of a search of this kind as a function of the lifetime. And you see again this elbow shape where you have in the area of this is in nanosecond. It's hard to see the axis. So around 2 to 3 nanoseconds, these are the case in the middle of the tracker, you get the highest sensitivity because the track disappears. When the lifetime is too short, then the chargino is not even reconstructed, it decays too quickly. So this is almost like a neutrino. And if the lifetime is too long, it never disappears. You don't get missing outer hits. And this is like a heavy stable charge particle. So it does not disappear. We go to the next type that are decays in the calorimeters. And then you can have decays in the E-cal or in the H-cal. And at this stage, the long-lived particles have traveled a microscopic distance. And possibly they have also traveled slower than the speed of light. And in this case, the decay products will reach the E-cal with a time delay. And then here the time delay could be from picosecond to nanosecond. And in addition to this delay, the long-lived particles will leave no information in the tracker. So now displaced vertices can be used, DE, DX can be used, or any impact parameter information anymore. So one has to use other handles to reconstruct this. In particular, for a delayed jets, this would be a jet with no inner tracks. So you would have just a long-lived particle that decays, leaves the tracker and decays and leaves no information. And then for the case of the photons, photons already do not leave tracks in the inner detector, but instead they will enter the E-cal at abnormal angles. So this is a typical photon produced in a sonomolar process. And if it's from the decay of a long-lived particle, in this case, a neutralino, it would travel the neutralino, and because it travels a larger distance than what it would be a prompt object, it would enter just the E-cal with a strange angle. So these properties are exploited in the searches in combination with timing information. And this plot, what it shows is the time resolution in the E-cal. So the time resolution is here in the vertical axis. And here it's a measurement of the effective amplitude of the energy deposited in the E-cal. So this is a measurement of a proxy of the quality of the measurement in the E-cal. So as you can see that for the best crystals, you get a resolution in the time that is of the order of better than 200 picosecond. So this is the metric to keep in mind. So you have sensitivity to less than a nanosecond with the E-cal. So the way that this would work, and then now I'm going to talk about delayed photons. The signature that is considered in this publication is to search for a long-lived squark, for a long-lived neutralino. So this, you have a squark. This is a prompt squark that decays into a long-lived neutralino. And then this decays into a delayed photon and then a gravitino. And here the gravitino it will be stable, and it could be also a dark matter candidate. But the important point is that here you get a delayed photon just because of the lifetime of the neutralino. And here what you see is that here photons entering in abnormal angles have been selected already, and you see the time distribution for a signal of this kind. And you see that there is a very long tail towards more than several nanoseconds. And this is much more than the E-cal resolution. And here, the dots here is the prompt data. So this is the background, and you can see how you can distinguish this clearly. So here the result is in the plane of the lifetime and the mass of the neutralino. And again, now the bulk, or just the highest sensitivity, is now in the meter length, and this is because this is where the equal is. And you see that for smaller lifetime, then the photon is not delayed, and then it mixes with the bulk of prompt photons. And then when the lifetime is too large, then just the photon is produced after the equal, and then you don't have timing information. So you lose also sensitivity. Then moving farther away, this is quite similar search. This would be the case for a delayed jet instead of a photon. So you can have, for instance, a long-lived gluino that decays to a gluon, and then again a gravitino. And in this case, this is also interesting because if you have a very long-lived gluino, it can hadronize, and it can form a hadron of supersymmetric particles. So this is called a R hadron. So this can lead to a funny way of BSM object. But the R hadron is not discussed in the publication. Well, it's just briefly discussed. In any case, there is a delayed jet, and this is what is used to discriminate against background is the time delay of this object. And this is the distribution that is shown here. So this is the time for the delayed jet candidate in nanosecond. And you can see that as you go away, like 3 nanoseconds away, the background is just tiny. It's less than 1 event. And here, this is nice because we can have a breakdown of what kind of events we have several nanoseconds away. And you can see in blue that this could be a cosmic ray, a muon background that can be reconstructed as a jet in the calorimeters, or you can have jets from satellite bunch crossings. So these are bunch crossings that are happening after the nominal bunch crossing. So this is why you have this structure every 5 nanoseconds. But again, this can be easily rejected because these are jets with very special properties. And then here we have the signal of 3 long-lived gluinos of actually very high masses. These are 2.5 TeV. And again, this is the same problem that I discussed. It's quite hard to do hadronic searches at low mass. So here the result. So the result for delayed jets, again, here show the line for 1 meter. So this is where this search has the highest sensitivity. And then just for reference, here I wanted to show another search. And this is a search for a similar signature in the tracker. And you see how searching for the same object at different subdetectors, it can complement the coverage in the lifetime spectrum. So this is why searches for long-lived particles require different approaches at different detectors that you can cover any lifetime. Because as I said, the lifetime parameters, so everything should be explored to have the full coverage. And then finally, I'm getting to the end of the seminar. I'm going to discuss the muon detectors. So this is actually what I'm working on at the moment. And then here we have the muon detectors. So these are the DTs, the CSCs. And typically now you go to the farthest displacement and you would have a neutral object, for instance, that decays to a pair of muons, and then you reconstruct them in the system. One clear background here is going to be the cosmic ray muons that are hit in CMS continuously. So one example of this kind is to search for displaced muons only using the muon detectors. And this is interesting for 2 reasons. First is that you can cover the highest volume because the muon detectors are at the outside of CMS. So the radius is about 7 meters, and then the length in C is about 10 meters. I already discussed one of the models that can lead to this type of signature. It will be a pair of long-lived dark photons in rare Higgs decays. So you get displaced muon pairs. And what is important with the muons is 2 things. The first one is that with the muons, you have lower backgrounds. So you can have triggers with low PT objects. And this means that you can probe low long-lived particle masses. And this is going to be below the mass of the Higgs, half the mass of the Higgs. So you can really search for long-lived particle decays of the Higgs with high efficiency if one relies on muons or leptons in general. In particular, for what concerns the muons, as already discussed, that you can extend sensitivity up to several meters. And then you can reconstruct the muon with and without using the tracker. And this is interesting for long-lived particles because for a given muon, if you have both reconstructions, so you have the muon and also you can find the corresponding tracker part, you can use this to veto prompt muons from standard model background. Now, this is very powerful to suppress background. The downside of using the muon system is that you have a low efficiency due to the trigger. And this is what they show here. So you can see that the efficiency, how rapidly it falls as you go out in displacement. And then I already discussed the background of cosmic ray muons. So here I show a limit on the production. This will be the Higgs to long-lived particles to the muon final state as a function of the lifetime. And here you can have sensitivity even up to 10 meters. And these are really decays outside CMS. And these are decays that are prompt. And again, this is the only case where I've discussed long-lived particles of low masses. Okay, so I'm going to conclude briefly talking about LLPs in the future, and these are put the planning for the high Lumi LHC, including the Run III. And this, I think, is the latest one, but it's still contingency model or the COVID to see how this changes. And connected to the last slide about the displaced muons, this is going to be a bit of the propaganda of what I'm doing or what I plan to do. This already discussed how this efficiency drops very rapidly as you increase the displacement. But if you look carefully, you see in red, so this is trigger efficiency in black, in red, you see the reconstruction efficiency. This pretty much follows the trigger efficiency. So what this means is that you can reconstruct the objects once you have triggered them, but the problem is that you don't trigger them. And the reason why you can do this offline but not online is that the muon PT at level 1 imposes a beamspot constraint. So you assume in the level 1 trigger that the muons come from the beamspot. And the reason why this is done is that this improves the resolution for prompt muons. So this, for instance, would be Higgs to 4 muon decays that I discussed already, the mass. So this improves the resolution, and this is important to use here. But for very displaced muons, this just bias the PT measurement, and then you artificially measure a low PT that is just below any threshold. And you don't trigger those events. So essentially you throw most of signal events. And this means that there's a significant signal efficiency that can be recovered. It's known how this can be recovered. And if this is done, you will improve the sensitivity beyond any luminosity scaling to go almost 1 order of magnitude if this is recovered. For the highest lifetimes. So currently I'm working on this, on prepare a search for Run III data without this bias constraint. And for this, I'm currently looking for a PhD. So I have an open call in Inspires. And the deadline is at the end of the month. And then finally, outside my planning, so what I see for Run III and beyond in long-lived particle, and this is just my personal guess. So for Run III, this is between 22 to 24. This is the time for new idea because there are lots of signatures with room for improvement. And I think the main improvements will come from creativity. And what I mean by creativity is that now there is time to develop new dedicated triggers for LLPs that could be done in the past, just they were not done because it was not the priority at that time, because the inclusive searches were still more important. Then we can use clever reduced data formats or ways to store the data to allow the deployment of triggers for low masses. So how to go to low mass, essentially. We're just now starting to explore widely timing information. I've discussed the eCal, but you can use muon system or you can use it in a more smart way. And then I see for the future more searches combining the production of long-lived particles with prompt objects. This is interesting because you can use them for trigger. And then for the future, for high-lumi LHC, this is from 27 onwards, you would combine all these ideas with some real detector upgrades, like inclusion of tracking at level 1. This would be a game changer. And then there's a discussion of a dedicated timing detector that this can be used, of course, to trigger on long-lived particles. And then there are plans to extend the ETA coverage, like the tracking and the muon detectors that also benefits long-lived particles. But this is common to prompt. And then finally, I haven't discussed, but this is a topic by itself, what happens with long-lived particles that decays outside the detectors. And in fact, this is possible. In CMS, this would be missing ET in most of the cases. But there are many plans or many proposals to build dedicated long-lived particle detectors meters away from Atlas, CMS, and LHCb. And here, I just wanted to quote some of these proposals, like Phaser. This has been already approved after the Atlas is going to detect long-lived particles produced in an Atlas interaction point. Matusla, this is a proposal for CMS. CodexB, this is for LCB and Nubis, this is also for Atlas, I think. And then there's Millikan, that this is for fractionally charged particles. So there are many proposals, there are even many more that are now under discussion because this is a very active field of LLP detectors. So this brings me to my summary. So the probably main conclusion is that in view of the results of searches up to now has boosted the field of searches targeting challenging experimental signatures. And then one prominent example of this kind are searches for BSM particles with macroscopic lifetimes. And this is important because the LLP phase space is broad and largely unexplored. I think this will make LLP searches a vibrant field in the coming years. And the reason for this is that there is a large room for improvement for Run III and beyond. And this goes beyond any luminosity scaling. In particular, new triggers, reconstruction algorithms, many guys are coming and applying machine learning to search for these objects, theory ideas, some even crazy ideas. And in general, clever ideas are going to be needed to fully exploit all the detector upgrades that will come. And just the idea is to explore the complete slew of long-lived particle signatures. And then just to conclude, here put the usual summary table, but now for long-lived particles. This is increasing, but still there are many holes in this chart. And it's even hard to plot in one summary plot and have the complete picture. So yes, I think this is all I wanted to say.
Thank you very much, Alberto, for a very, very brilliant talk.
Thank you.
So are there, well, let's start with the questions. Just raise your hand in Zoom and I'll give you pass. And let's stay with English since the seminar has been in English, though I think we are mostly Spanish, to be honest, in the list.
Yeah, you can ask in Spanish. This is fine. I would answer in English, just that everybody understands. But...
Okay, so while people get, okay, Begoña?
Okay, so Alberto, thanks a lot. This has been a really didactic and interesting seminar. I like it a lot. One general question. You have been stressing the characteristics of the detectors, the triggers, the reconstruction programs, and so on are really important for this topic. In this sense, are there differences between Atlas and CMS in terms of the sensitivity that they can have to each of these analyses? Because Atlas is larger. So that means it can go or track decays which are farther away from the interaction point. Is it in the end that the case or not?
Yes.
Because, okay.
This is a really good question. So this is one of the fields where there are more differences between Atlas and CMS. As you said, Atlas is bigger. So usually for them, it's easier to cover larger lifetimes. They have a better PD resolution, typically if they only rely on the muon system. So usually they're quite good for searches with the muon detectors. In particular, they have many searches for hadronic decays into the muon system. So you can imagine a jet inside the muon system. So this we don't have in CMS at the moment. There are people working on it, but we don't have. In general, we are better with searches in the tracker. So displaced jets, displaced vertices. And the reason for this is that they have many problems to reconstruct tracks that have a large impact parameter, because in their schemes, when they produce their data sets, they remove all these tracks. And every time they want to do a search for displaced objects, they have to have a special reprocessing that includes these tracks. So they have to make a bigger data set just to make these searches. So this makes making long-lived particle searches in the tracker already a challenge, because they already need a special data set. So there are many differences. For example, in timing, CMS has already 2 searches with timing. Atlas doesn't have searches with timing. So this is one of the questions, just the complementarity with Atlas, because there are many differences, and it can happen that a long-lived particle, if it's discovered, it might not be possible to discover it with the other experiment, and vice versa. This is much harder with a prompt signature. So it's very important to at least, and this is what is done. Usually the people try to copy what Atlas is doing and vice versa, just in case they can do something that we cannot do.
Okay, thanks, Alberto. Very interesting.
So, Alberto, just to follow up while more people think more questions. And what about LHCb? I thought that they could, at least in some part of this space contribute a little bit, or is it too limited by the?
So yes, yes, this is also a good question. LHCb, it has, so they rely a lot in their velo, so the vertex locator, and this is very close to the IP. And the moment that they go away from the velo, they have problems because they have very low efficiencies. So usually for large lifetimes, they are not really good. Now, for short lifetimes and small displacements, for example, the dark photons, just a typical displaced C prime, they have the strongest limits because they can really go low with the triggers, and even they have a triggerless system for Run 3 that they would record all the collisions. And I see LHCb as a really strong competitor for long-lived particles that are produced in BDKs, for instance, or low masses in general. If you go to TV objects or long-lived particles producing Higgs decays, I think this is the kingdom of Atlas and CMS. But for example, for HNLs, they're going to have a strong limits, I suppose. Those ones producing BDKs for dark photons too. So it really depends. For HCP or Charginos, they are not that good.
Okay, thank you very much. Juan Pablo.
Yes, can you hear me?
Yes.
Yes, Juan Pablo.
Okay, so very nice presentation. Congratulations, Alberto. I have 3 questions. So should I ask the 3 of them at once or one by one? What do you prefer?
Go one by one.
Okay, good.
Unless they are related. If they are related.
No, they are not. So the first one is I like it's first a comment. I like the thing, the way you express the need of creativity, and you say that the word creativity in physics is I think it's needed, and I agree with you.
Well,
and yes.
Yeah, no, continue.
And the fact that you have proposed one new thing regarding how to have more of this type of particles by just not imposing this beamspot constraint is a very nice and easy, I think, simple. No, not easy, simple. I don't know how easy is to implement this in the CMS software code, because I have no idea. Hope it's not too difficult, but this is a nice and easy, because easy, not a simple thing to do, and probably, as you say, would increase the statistics, but a non-negligible amount. So how did you get the idea?
Well, no. It's a good question. So as you saw in the plot that I showed of the efficiency, you see that it drops rapidly. But then you start to find what failed to have such a low efficiency, and then you realize that it was the level 1 trigger. And then inspecting the events that failed, you would see that it was clear that the measurement at level 1 was too small, because once you have a very displaced track, if you add an additional point at the beam spot, then the PT is just tiny, it's like less than 5 GB. And then all the events would fail. And then, because this is something that you add, I mean, is something that you have to remove, right? It's just that you get a worse resolution. But in principle, the concept is not complicated, as you said. And this is something that is important for prompt, just for Higgs to mu. But if you remove it, and then you can deal with the background, because you have worse resolution but more background. This is just a complete changer for displaced searches, because as you see, you throw most of the events away. And this is how, like, just talking with the level 1 people, then now they are working. I'm not implementing this myself, so I'm just transmitting the community that the level 1 experts that they should allow for this possibility, because this is harming long diff particle searches. And then I would just build the trigger and then build the search, and then profit from this. This, it really is a simple thing, but it would just completely change the analysis.
Yes, and as you said, it's not just a matter of creativity, it's creativity and something else. Very, very tough work.
But just connected with Atlas, Atlas has the same problem. So this would be an example that if this is done and Atlas is not doing the same, this create an asymmetry. Probably they are also aware of this limitation and they are working on it. But you know, these are things that were not really thought when the system was designed, because it was keeping in mind prompt objects like the Higgs. But now that one is extending to more exotic signatures, then you want to have this possibility, because you're not going to change the LHC. So we have to deal with the LHC that we have, the detector that we have, and then we should exploit all possibilities.
Okay, thank you, Alberto. Now the second question. Let's think of a particle, a special particle that decays like a K-short. So are you thinking on trying to develop a special tracking pattern recognition or something like that to try to improve your search in this limit?
But this would be, so what are you keeping in mind, to measure K-shorts or to reject them as a background?
No, the major background probably, but not necessarily the current pattern recognition is thinking of K-shorts. I don't know. Maybe they are already also doing pattern recognitions that are thinking about K-shorts, but probably
in long diff particle searches, there's not any special treatment for K-shorts. Usually, their decay products, like the invariant massive decay short, is vetoed in some cases, like LHC is doing this. But in general, most of them would be trapped or be measured in the calorimeter when they decay. The decay products are just outside the detector, and they are not really treated specially for many of these searches.
Well, maybe let's not put the example of decay shot, but a particle that decays within the tracker and probably within the outer tracker. So just a few layers.
Yes. So
Maybe you
okay,
mean...
okay, yeah, now I understand. So you would have a neutral that decays in the outermost part. So this is actually one of the yes, I understand. So usually the more you go farther away of the tracker, you go outside the pixel, you have less information, and then it's easier to get background for combinatorics. If you have too few hits, you can start building displaced tracks easily. So you can have a very high background. So now the people are working on relaxing the way the tracking is done, such that you increase the efficiency to reconstruct very displaced tracks. So this is also a very active field of people tuning with the track reconstruction to get a higher efficiency. But at the moment, there are no searches that do tracking outside the pixel. So this is one of the things that I think we would see in Run 3, but we haven't seen so far. Other problem is that you can have decays from material interactions. You can have displaced tracks produced inside the tracker material. So you want to have good quality tracks that you can suppress them. But if the invariant mass is high and you're convinced that this is a displaced vertex, I mean, this is definitely one of the things to do. For instance, for the muons, this is easier. And this is something that we're trying, because the muons, you would have also information from the muon system that even if you have few information in the tracker, this is already enough, even if it's produced outside the pixel or then at the end of the tracker. And then this is easier, and this is something that we do at the moment. But for just for a displaced jet, this is more challenging. But this is definitely something that it should be done.
Yeah, it's a nice example. The muons would be the first thing to try.
For the muons, this is really good, because already having few tracker hits, we see that this already improves a lot the PT resolution of a muon reconstructed in the muon system. It just a game changer again. So.
Yeah, let's try to make it short. I saw your plot of the EDX of standard model particles versus other particles, and I see maybe a factor 4 or 5 difference between the two, the standard model versus non-standard model. Are we capable to cope with this, our detector? I should know, but I don't. Sorry.
So yes. So one of the things that the plot doesn't show is construction efficiency. And for these particles, the reconstruction efficiency is typically lower. And it definitely, if there is a high rate of these BSM particles, I mean, it's great if they're produced, but it can do. I don't have numbers, but I'm pretty sure that the tracker is not really designed to have a high dose of these particles. At least it was not designed keeping this in mind. So tracking efficiency is usually lower, but you don't want to produce thousands of these. You just need a handful of these strange events. And you have the discovery, and then you have to prepare an upgraded tracker that can measure long-lived particles.
Right.
This will be great news, but yes, so the tracker is not designed for such a charges, and the tracking efficiency is lower.
That's it. Thank you very much. Very nice.
Then I think, thank you, Juan Pablo. So I think we have a last question by Begoña, and if there is something else urgent, we can also have it, but I think let's go with Begoña first.
Thanks. No, mine is really short. It's related to Pablo's second question. You have been talking all the time about disappearing tracks, but I guess, and also maybe related with this question from Pablo, one can also talk about appearing tracks or appearing particles.
Yeah, so the main, you would have disappearing tracks if the long-lived particle is charged. So then you measure it and then it disappears because the decay products you don't see. And then appearing tracks, it will be just a neutral particle that decays into charged particles, so like a dark photon. So let's say most of long-lived searches would target appearing tracks or just displaced tracks. And then disappearing is typically for charged ones.
Okay, so they are included in what you call displace tracks. Okay.
Yes, I think
I see.
I mean, there are things like emerging jets, that this is where different displaced vertices appear at different displacement. Also, this can be called an appearing track, but probably if you think of the analogy with the disappearing, it's just going from neutral to charge. So whether you measure the long-lived particle itself or the decay products of the long-lived particle.
Okay, thank you very much. I actually have more questions on the implications for phase 2 and so on, but I think considering it's past 12, I think unless there is something urgent from somebody in the audience, which doesn't seem so, I think we can wrap up. Alberto, thank you so much again. It's been a fantastic seminar, so very much appreciated. And we had hoped to have you presently in CIEMAT, but you know that with the situation it is not possible. So thank you.
I really wanted to go, as you know.
Yeah. So next year, when things are back to normal, we can hopefully have you again. So thank you so much to Alberto for the very good seminar. Thank you so much to everybody who connected and for the lively discussion. And see you soon. Have a nice afternoon.
Bye, everybody.